negative 1 to 1, it turns out we know that that's an exact. Okay, so the manipulations I had to do to make that work turned out to be pretty simple, right? So I had to ensure that this thing was positive, and I had to ensure that this thing was negative over the region that I cared about. Okay, so it turns out Lyapunov analysis is about checking positivity of functions. Okay, Lyapunov stability analysis in this case is directly related to checking the positivity of a function. So let's think about, it happens to be a polynomial function in that case. So let me give you a couple quizzes here. So is 1 plus 2x squared greater than 0 for all real x? That one's pretty easy. And that's got to be positive, right? What about this one? So that one's a little harder to think about. I'll go ahead and show you that it's easy to think about if I just rewrite it in this form. That's just factoring out in a different way. I can write it in this form, and now I can see, well, this thing's positive, this thing's got to be positive, this thing's got to be, that's a sum of squares, that's got to be positive. So I'm all set. What about that one? This is not artificial, this is actually the first pendulum example I'm going to run. Let the computer solve. Okay? What do you think? Is it positive? I thought you might guess it was positive, so I subtracted 2. Okay? So if you add 2 back in, then it's positive. But so that's harder though, but luckily the computer's going to run through that really fast. Okay? And here's how it works. It's a sum of squares optimization. Okay? It turns out that the decomposition of a polynomial into a sum of squares decomposition turns out to be something we can do really well with positive semi-definite programming. Okay, so here in the example, if I were to just rewrite this in a matrix form and put some vector of monomials here, of things that are 1x here, and write a matrix times that same thing, then as long as this matrix is positive semi-definite, then that is a sum of squares. That's exactly the same as me writing out the factored version, saying that this is a sum of squares decomposition. That's this. Okay? And so more generally, if I had chosen a different monomial basis, it could be that I have to search over the class of semi-definite matrices, subject to the constraint that these equality, this side equals this side, which puts some constraints on what those coefficients, because the only one that can contribute to this term is A11, so A11 had better be 1, so on and so forth. But here's the trick. The set of positive semi-definite matrices is a convex cone. It's a convex set. So I can, if you have 2 positive semi-definite matrices, you add them together, you get another one. That means it's a set I can search over very efficiently. And these are linear constraints on that convex cone. So it turns out we have